Good morning, everybody. Hopefully you had a lovely, lovely long weekend, had some turkey and some time with your friends, family. If you could, please give me a green check mark in chat, and I'll make sure everybody's with me. Anyone get up to anything exciting this weekend? Go anywhere fun? Visit someone or do something? Have any cool horse riding stories or anything like that? Anybody compete in anything? Got a few seconds here while people give us some green check marks. Haley, you did. Did you care sharing with us what you did? You just had a good weekend, Haley. Watch the Blue Jays crush the Rangers. I was a little curious as to whether or not they would pull it out, but they did. And game 5 tomorrow night. Be exciting. Even went to Calgary. That's cool. Calgary's a nice place. There's a couple people with no green checks, so we'll just get those in, and then we'll get going. Grandparents, fancy brunch. That sounds like a good weekend. Can't underestimate a fancy brunch. Abby, were they in town and your grandparents live in Kelowna or somewhere else? I think that's everyone in now. Perfect. All right. Well, Abby puts in where her grandparents live. We will get going here. Clean out the foam pit at the gymnastics center. Andrew, I hope it's not the one out in Rutland by the Y, because my little guy, he plays in that pit a lot, and I don't want to know what's at the bottom of that pit. So you're going to have to keep that story to yourself. So I've been in that pit. Wouldn't be surprised if there was small children stuck at the bottom. All right, where are we in the course? On Thursday's class before the weekend, we finished up Unit 2. So I had a chance to check in on Unit 2 this morning, and a bunch of you have yet to submit the learning guide, which I understand was a lot of work. And I feel a little bit bad about that, that it's taking a lot longer than we expected. So we're going to adjust things a little bit for Unit 1, which is the next unit, which we're going to start today. And we're going to just, we're just going to keep plugging away. So if you could get in that learning guide today, that'd be awesome. I'll get you the code, hopefully by the end of the day, so you can write the test before tomorrow. And I was kind of hoping that all of the tests would be written before tomorrow. And there's a lot of you who haven't done quiz number 4 yet, and a few of you haven't done quiz number 3 yet, which was due a long, long time ago. So we got to make sure we keep moving in the course, because if we get a little bit behind, it's going to start to snowball, because this next unit's a real short one. It's not terribly difficult. I'd say it's probably a little bit easier than unit number 2 that we just completed. So I want everybody to stay on track, because we'll likely finish this unit this week. We might, we only have 3 days this week, right? So maybe we'll have class on Monday again and finish up Unit 1, but it's definitely not a long one. So I've adjusted a few things for Unit 1. Just wanted to mention. You can see up at the top here, I have learning guide to print and complete. So that's the same learning guide as you guys did for Unit number 2. So you guys will print that fella off, and you'll complete that. And submit it before the test at the end. I put all of the lessons together, and I put this capital all with 3 stars next to it. So if you guys are having issues printing and things like that, they're all, for the entire unit, are all there in one file. So you don't have to do one at a time, which I thought might help you guys out a little bit. And then all of the practice sheets from all the lessons are here too, all together. So they're, again, all one printout. I wanted to spend a little bit of time talking about what we're going to do in terms of work for this unit, because I know the last unit was a lot of work because the questions were a little bit longer, and I kind of underestimated how long the questions would take. So I had you guys do the practice, and I also had you guys do the learning guide. But For the unit number 1, it's a little bit more straightforward. Doing a lot of practice isn't really going to help you. You're either going to understand kind of the definitions and things or not. So what we're going to do this time is I'm not going to require you guys to do the practice because they're just a bunch of questions that are kind of similar to the learning guide. So as we go through the unit, at the end of each lesson, I'm going to go to the learning guide and say we should complete these sections. So kind of for homework, we're just going to do the learning guide this unit instead of both the learning guide and the practice. So I'll talk about it again at the end of the lesson. So hopefully that makes a little bit of sense. Today we're going to just jump right into lesson 1 and I'm going to go through that. And I have a feeling we might have some extra time. So I might get started on lesson 2, but we'll see how far we get. So here we go. This is unit 1, lesson 1. And we're talking about irrational and rational numbers. So you've likely heard of these things before, but maybe not spent a lot of time kind of thinking about them. So we're going to look at them in depth. So at the very beginning, the formulas for the area and circumference of a circle, so we just finished that in our last unit, involved pi, Greek letter, which is not a rational number. Because it cannot be written as a quotient. Now, does anybody remember what quotient means? We don't often say quotient. Usually we say something else when we mean quotient. Anyone remember what quotient means? There's a couple of us typing in chat there. Quotient's just a fancy math term for a division question, that's right. So quotient just means division. Or we can write it as if we want to think of it as division or a fraction. So we are going to get into a lot of kind of vocabulary this unit. And it kind of seems weird. Usually when you think about math and vocab, they don't really go together. But it's just kind of the nature of this unit. We're talking about numbers and number types and things like that. So there's a lot of words that are going to come up, and you really do need to know what they mean. So I know it's just basic memorization, and I'm not a huge fan of it, but it's just kind of a reality of it. So I'm going to try to make it as easy to understand as possible, but at some point you may have to sit down and start thinking about what the words mean and what sort of numbers are associated with them. So we'll do a bunch of examples. It says try this work with a partner. Instead of working with a partner, I want you guys to do it. And we're going to spend a lot of time typing into chat and stuff. So anytime you see something like the square root of 100, we're going to have to represent that in chat some way. Because when we're going through these questions, this unit's all about these radical signs or square roots. So a couple ways you can do it in chat is if you write something like SQRT would be a good abbreviation for square root, and then you could write like SQRT 100, which would mean square root of 100, or something like along those lines. That way, if you are talking about a square root sign, I am able to kind of understand what you're talking about. So SQRT would be a good abbreviation for square root of 100. So what I want you guys to do is, just on your own, I want you to plug a bunch of these numbers here. These are the rational numbers, and then these are the not rational numbers or irrational numbers. I just want you to fire a bunch of those into your calculator and see if, like a pattern emerges, something that you kind of notice. And that's the first question here. Question A says, how are radicals that are rational different from radicals that are not rational numbers? So I'm going to give you guys, like a minute, fire a bunch of those in, maybe write down a few of the answers, and then see if you can answer A. You could even throw it into chat if you want. All right, so a few of you look like you're typing. Hopefully you've had a chance to put those in. Maybe you see some patterns emerging. Maybe you've talked about rational and irrational numbers before and you kind of understand what these things are already. You probably should see some patterns emerging once you start finding the square roots of some of those numbers or squaring them even. Nobody's really keen on throwing anything into chat. That's fine. Some of you might be typing and just be a little bit slow on the lag here. If I take the square root of 100, I end up with 10. And if I take the square root of 0.25, I should get 0.5 or 0.5. Let's make sure I get that right. It's 0.5. The cube root of 8 is 2. 9 over 64 should be 3 over 8 simplified. You might have written it as a decimal. Abby threw an answer into chat here. Let's see what Abby says. Maybe shrink that a little bit. There we go. The rational ones equal numbers that have an end, but the irrational ones go on forever. That is exactly what I was thinking as well. So when you say they have an end, what you really mean is they terminate. So this is another word that is going to come up. So let's look at these ones. Square root of 0.24, that's going to be 0.489897. And it goes on forever. Square root of 2, that's a common one that we'll see a lot. And that is 1.41421. And that keeps going forever. And you'll notice that these guys as well, they continue on forever. So there's a couple distinctions that we'll see here in a second. We end up with the idea that there's rational and irrational numbers, and just because it has a decimal that fills up your calculator window doesn't mean that it's an irrational number necessarily. So there's a couple kind of, we'll almost call them exceptions to the rule. Isabel's asking, how do I put the cube root of 8 into my calculator? And this is kind of where we're going to have to learn how to use our calculators. The cube root of 8. So, and Devin, same question. I had a feeling a few of you would. My calculator is a Sharp calculator, this little guy here. And I have a button that looks like this. So I have a button, and mine says square root, maybe make this a little bit bigger. It has a little X, and then it has a square root sign. And that is what the button looks like on my calculator. Some calculators will have a cube root button on them. This one doesn't. Oh, yes, it does. This one actually has a cube root button. So you probably have a button like that, or you might have a button that looks like X to the Y or Y to the X, something like that. So these are the kinds of buttons we're looking for. If you have an X to the Y, right above it's probably something that looks like the X in front of a square root sign. So the way my calculator works is if I want to take the cube root of something, I have to put in the 3, and then I have to hit the little X with the square root sign, and then I have to put in 8, and that should give me a 2 in my window. So you have a cube root button, but it's on my 0. So Taylor, you probably have a shift button or a second. On mine, it's all color coordinated. So some of the functions are yellow, and then the other ones are green. And Alex is asking a really great question, which is, if a number fills up our calculator, how do we know if it's not an irrational number? So we'll get to that in a second, Alex. That's a good one. Really good question. I'm going to answer a few of the questions here in the work. And if you haven't found that cube root button or the X root button yet, I assure you, if you have a scientific calculator, it's on there somewhere. It just might not look like the one I drew. That's just what mine looks like. I have my TI-83 here, and this one doesn't even have the button that I just mentioned. The button I use on this calculator is actually this little guy here. It's called a caret. Looks like a little hat. And we'll talk a little bit more about that. You can see nowhere on this whole big fancy $100 calculator is there an X to the Y button, which is kind of weird. That's just how they do it. All right, so the first question asked, how are radicals that are rational numbers different than radicals that are not rational numbers? And this may not make a whole lot of sense right now, but I'm just going to put it in like this for now. And we're going to write they can be written as a fraction. And you might be thinking, Mr. Borden, we ended up with like just whole numbers, and how can they be written as a fraction? So up above, for instance, we took the square root of 100 and we ended up with 10. And you're thinking, that can't be written as a fraction, but it kind of can. If we write it as 10 over 1, it can be written as a fraction. So sometimes if we end up with just a whole number, we're going to have to think a little bit, oh yeah, I could put a whole number over 1 and it would just be the same thing. Taylor asked about putting fractions into your calculator, and generally speaking, Taylor, calculators won't deal with fractions well. Some calculators will allow you to, some will not. So my Sharp calculator here, it has let's see if I can find it. Usually, sometimes calculators have like an A over B button, and you can put it in as a fraction. But generally speaking, we'll just find the decimal and then put that into the equation we're dealing with. So it's kind of a two-step process in your calculator. The thing with calculators is they are awesome, but they don't know order of operations, which is kind of silly when you think about how amazingly powerful they can do, like enormous calculations, but then you ask them for a simple process like BEDMAS, and they just can't process that. So the calculator relies on you to do BEDMAS as you're entering things. So that's kind of one of the hurdles we run into when we rely on our calculator. All right, so question B here asks, which of these radicals are rational numbers and which are not rational numbers? How do you know? So we're going to have rational numbers. And if we take the square root of 1.44 here, what do we end up with? If we take the square root of 64 over 81, and again, you could just do the division first and then take the square root of it. The first one's rational, all right? So what did we end up with there? Square root of 1.44 should be equal to 1.2, I believe. Thank you, Ava and Taylor and Abby. All right, so we got that one. 64 over 81. This one's maybe a little bit tricky. Now, we haven't talked about the rules for radicals or anything yet, so this is going to be the same thing as 8 over 9. So if you plug that into your calculator and just did the calculation, you should end up with 1.125. 60. So 0.8888888889. This is one of the kind of exceptions that we run into. If we have a decimal, I'll write it as a decimal like you guys did, 88888. What's significant about that 9 in the last digit of your calculator window is that your calculator is just rounding that for you. Really, this number is just 0.888888, continuing on forever. So really the 9 is your calculator doing some rounding for you. So when we have a decimal that goes on forever that has a pattern or a continuation like 0.88888, that is a rational number. And the reason that is a rational number is we can write it as a fraction. Now, I believe that's a Math 9 idea, converting repeating decimals into fractions and back and forth. So definitely have that one. The cube root of negative 27 should give us negative 3, which is just a whole number. And it's kind of where we end up. So square root of 4 over 5, that's not going to give us a terminating decimal, and the square root of 5. So both these things are going to go on forever. So when we have our rational numbers, we're going to end up with these ones. And the only tricky one is this 0.8888, because we can write that as a fraction. So Taylor, the reason we define rational numbers the way we do, or irrational, is that we don't say if it has a decimal that doesn't end, it's irrational, because that's not true. If we have a repeating decimal like 0.88888, then we know that we can write it as a fraction. So you guys did that in Math 9, whether you remember or not, possibly. So when we talk about the definition of a rational number, we always say if we can write it in the form of a fraction, we call it a rational number. And because repeating decimals can be written as fractions, they fall under the rational numbers category. So they're kind of the exception that I was talking about before, where you can go through all these calculations. If you end up with like 0.33333333, you can write that as 1 over 3. And that's a rational number because we define it as something you can write as a fraction. So I'm going to go back and we're going to write in here their solutions can be written as fractions. All right, question C asks us to write 3 other radicals. So we're talking about square roots, cube roots, that can be rational numbers. So maybe you can throw a few into chat and we'll see if we can guess these. Now, keep in mind, we haven't talked really about any of these very much, so if you get something wrong in there, it doesn't matter. We're just getting started, so we're just kind of formulating our ideas. So we need to, for part C, write 3 radicals that haven't shown up. So we need a square root of something that will give us a rational number. So the square root of what will give us a rational number? Now, Ava, you put in a third, which is a rational number, but this one asks for a radical. So we want to go. Taylor, brilliant. Square root of 4. That is definitely a rational number. Which is good. Anybody else? Kind of maybe see a pattern developing here. Square root of 4, I like it. That's a good one. Square root of 900. Going big on us here, Abby. Yeah, that is definitely a rational number. Square root of 81? Yes. Square root of 16. Oh, you guys, you got it. So what you guys are all doing right now is picking perfect squares, which is really a great idea because those are all of our rational numbers. Jade, square root of 16. Taylor, square root of 400. So You guys are on top of it today. These are all great examples of rational numbers because they're all perfect squares. And we haven't talked about perfect squares yet, but you guys kind of hit the nail on the head here. So let's pick a few that you guys had in here. We had the square root of 4. That was a good one. I like that one. We had the square root of 900, which is going to give us 30. Square root of 81 is going to give us 9. Square root of 16. It only asked for 3, but we had a bunch of great ones, so we'll put them all down. And the square root of 400. So those are all examples of rational numbers. Why are they rational? You guys figured it out already. Why are they rational? Because they're all perfect squares and they all have, they don't contain decimals at all. So that's why they're rational. The last question here, just kind of getting things warmed up. 3 radicals that are not rational numbers, and why are they not rational? So we need some examples of not rational numbers. What do you guys think on these ones? So Taylor put this into chat, no decimal. I'm going to write that on the end. Because that is exactly what we're talking about. And it looks like we have the few irrational ones coming in. So Alex put in square root of 1. You've got to be careful with ones because square root of 1 is 1, which is actually rational, but 1 is a tricky one. So we'll let that one slide. Just because 1 times 1 is 1, that's square root of 1. So we have square root of 8, square root of 20, square root of 50, square root of 5. These are all really good examples of irrational numbers. How about a cube root? Let's maybe we could write that in chat as like 3 square root. I don't know if that makes sense. That might be a good way to represent that. I'm trying to think of maybe an easier way. If anyone has an easier way to think of the cube root of something. Or 3 root. That might work too. All right, so let's go with some of the examples you guys have thrown in here already. So we had 2 square root of 25, cube root, C root. I like that, Alex. That makes sense to me. If you put in something like CBRT, I would understand what that meant for sure. CRT, cube root, those will work. I like CBRT for some reason a little bit better. Just kind of triggers in my brain a little bit faster. Cube root of 25, these are all good examples. So you guys have a good grasp of this already. So what did we have? We had the square root of 8. I like that. That's a good one. Square root of 20, that works. And then there's a cube root of 25. Those are all good examples. One thing I wanted to mention about C that I didn't is you could end up with something like the square root, this is of 1.21. And you think by just looking at it that you're going to end up with some strange number. But the square root of 1.21 is just 1.1. So that's a decimal, but it stops. So that is a rational number as well. So we're going to run into lots of examples like that where you think maybe that the square root's going to give you some strange decimal that'll just continue on forever, but you're going to end up with a terminating decimal. It just ends. So you can write it as a fraction. All right, so we kind of have a little bit of idea what's... Taylor's asked a question about radical. To make sure, radical means number. Radical means the square root sign. So anytime I talk about a radical, that'd be like the square root of 2, that's radical. Square root of 72, radical. Square root of 1,321, those are all radicals. So the word radical just means square root. They're kind of one and the same. Hopefully that clears that up. And as I kind of mentioned at the beginning, we're going to run into lots of vocabulary. So we're going to write down some notes and things right now. This is maybe just a good reference. You guys can come back later when you kind of get into things and you're like, oh, I don't remember what a whole number was. When we need to kind of remember what those look like. So here we go. Radicals that are the square root of perfect squares, cubes, or cube roots, or perfect cubes, and so on, are rational numbers. Rational numbers have decimal representations that either terminate, just means they end, or repeat. So if they just keep repeating, like we had the example where we ended up with 0.888888, and it just was an 8 forever, that would be an example of a repeating decimal. We could end up with something like 0.123, 123, 123, and if that went on forever, that would be an example of a rational number. We could represent that as a fraction because that 123 just gets repeating. So if it doesn't terminate or repeat, it's an irrational number. That is correct. And Taylor, if it's like a pattern, we want to be careful with the word pattern because patterns could mean things like, I don't know, if we had 0.1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, that would be like a pattern, but that wouldn't be a rational number. So we don't want to think of pattern. But if we end up with the same thing over and over again, we would end up with a rational number. So Alex, if it doesn't terminate or repeat, like a repeating pattern. Yeah, you're right, Taylor. Yeah, just being a little bit more specific there kind of clarified what you meant for sure. So if it doesn't terminate or repeat, it's irrational. That means it goes on forever. There's nothing being repeated in the decimal there. And Taylor, yeah, exactly. So you guys got this. So this is kind of the textbook definition. Irrational number cannot be written in the form. I hate it when things write in the negative, cannot. Why wouldn't they just go with the positive? But anyways, they can't be written as a fraction, where m and m are integers and n is not equal to 0. This is all just really confusing textbook sort of stuff. What it really means is m and m are integers, just means numbers. And then n can't be 0. Remember the equal sign with a line through it just means cannot equal. The reason that's in there is we can't divide by 0. We can't have 0 in the denominator of our fraction, so they just have to put it in there to make sure everything's clear. The decimal representation of an irrational number neither terminates nor repeats, and that is almost exactly what you said, Alex, just before. So you had come up with the definition on your own. So when an irrational number is written as a radical, the radical is the exact value of the irrational number. We can use the square root and cube root keys on a calculator to determine the approximate values of the irrational numbers. So this kind of goes back to the solutions for the unit we were just in. When there was a radical in the answer, it was an exact value, and then I was talking about the decimal approximations. So if we had something like, just a really kind of straightforward example would be the square root of 2. If you think about the square root of 2, that's an irrational number. So if I put that into my calculator, let's just see exactly what I get, because I don't have that one memorized beyond a few decimal places. It's 1.41421. 3562, and that just continues on forever. So that is the decimal approximation of the square root of 2. The square root of 2 is the exact value because it's the square root of 2. That's easy. But when you put in your calculator is saying, that's not a perfect square. I can't just spit out 10 or 3 or negative 22. So I'm going to have to approximate that with a big long list of decimal numbers. And it's going to write in, fill in as many decimal places as it can. And then it's just going to run out of space in the window, and then it's going to round the last one and say, hey, you know what? This is as far as I can get. The window is just not big enough to represent this whole thing. And that square root of 2, as an irrational number, we know that it's not going to terminate, it's not going to repeat. So that just means literally the 1.414213562 is just going to go on forever. And there's been kind of contests and things like that in kind of dorky math land where people calculate as many decimals as they can of irrational numbers. So like pi, and pi is kind of the most famous irrational number, and people have calculated that to literally thousands and thousands and thousands of decimal places. And the reason they do that and the reason they're interested in it is if somebody could take a number like the square root of 2 or pi, and they could figure out at some point if it repeated or if there was some sort of pattern that developed like a million decimal places in, then we could classify it as a rational number, and it would change our way of thinking about math. But so far, all of the numbers we consider irrational, nobody's found one yet that kind of breaks the rule, that has a repeat in it somewhere or some sort of pattern that develops or anything like that. So yeah, that's kind of some math theory. So there are other irrational numbers besides radicals. For example, pi. That's one that we'll talk about a lot. So pi, we represent it as 3.14, which is kind of the common 2 decimal places. But it keeps going, right? 3.14159, and that's just kind of where I leave it. But it'll go on forever and ever and ever. So we can approximate the location of an irrational number on a number line if we don't have a calculator. So we're going to pretend for a second here that our calculator is broken and we don't have it, and we're given some numbers here. And we're going to put these on our number line. So here we go. We can approximate the location of irrational number on a number line. If we don't have a calculator, we use perfect powers to estimate the value. For example, to locate the cube root of 50 on a number line, we know that the cube root of negative 27 is negative 3, and the cube root of negative 64 is negative 4. You might not have those memorized, but those are kind of what we're going to work with for this question. So cube root of 50, negative 50 in my head, I don't know what that is. It's decimal, it's not a perfect cube. But I know 50 is between 27 and 64. So if I can pick a perfect cube on either side of it, I can figure out, kind of estimate what it is. So if you think about our number line here down below, maybe we'll put negative 4 over here, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Perfect. We'll go negative 3 here. So we know that the cube root of negative 64 is negative 4. So this is the cube root of negative 64 here. And this is the cube root of negative 27. And somewhere between these two values, we know that we're going to end up with a negative 50 in here somewhere. But where is it going to go? We don't know yet. So what is 50 closer to? Is it closer to the 64 side of things, or is it closer to the negative 27 side of things? Where is it going to fit in here? We're just going to have to kind of guess. So you can see in the example above, we've done the, if we take the 0.36 and cube it, we get 46. If we take 0.37 and cube it, we get 50. And I know what you're saying, Mr. Borden, we don't really have a calculator, so how are we cubing those things in our head? And maybe we had a calculator, but our square root button was broken, and then we ended up with only the square button. So yeah, it's probably closer to the 64, the 50 is closer to 64 than it is to the 27. So maybe we're going to find somewhere over here. It's going to be about 3.7. So this is 3.1, 2, 3, 4, 5, 6, 7. It's just going to be under 3.7. So it's going to be maybe somewhere in here, because we know that's negative 3.7. So sorry, I forgot all the cube roots here. Negative cube root of negative 50 is going to end up somewhere in there. Now we're estimating, so if you put it somewhere else, it's not a big deal. The only thing is we should know it's a little bit closer to the 64 end of the spectrum than it is to the other side. We're going to look at some more examples of that, possibly today, maybe next day. We have one more page here in these notes, so we'll just move on to that. This is where we kind of get into some of the examples and a little bit more vocab, which I'm not a huge fan of, but this is life. So which of the following is irrational or rational, and explain? So remember, we define a rational number as something we can write in the form of a fraction. So if we can write it in a fraction, then that means it's a rational number. So the first one we have here is square root of 49 over 16. There's many ways to do this. So if you want to go in your calculator, 49 divided by 16, get a decimal, and then take the square root of it and see what happens in your calculator, that's fine. If you want to think about it and think, 49, that's a perfect square. 16, that's a perfect square. Or if maybe the fraction could be simplified within the square root sign, you could do that. There's really lots of ways to go about this, because in the end, it's not asking what the decimal is or can you do the math. It's just asking, is it rational or irrational? And Abby wrote in chat, it's rational. And Abby is correct. And I'm going to write this. You guys don't know the rules for division of radicals yet, but if you think about it, the square root of 49 is 7. The square root of 16 is 4. So really, I could write this as 7 over 4, and that's a fraction. So it's rational. If you took, in your calculator, you did the decimal first. So you went 49 over 16, which is fine. 49 divided by 16 gives us 3.0625. And then you wanted to take the square root of that, and you'd end up with, I'll just maybe throw it up above here, is 1.75. Can I write 1.75 as a fraction? Because Taylor got 1.75. How do I write that as a fraction? Can you think off the top of your head, maybe, Taylor, how we could just quickly write that down as a fraction? 1.75. If we wrote down 175 over 100, that's going to give us the same thing. So I can write 1.75 as a fraction because I can write it as 175 over 100. Perfect. Taylor, you're all over it. So you guys seem like you kind of have an idea here. The next example, part B here, is the cube root of negative 30. So just off the top of my head, I'm thinking to myself, I know 3 times 3 is 9, times 3 is 27. So 3 cubed is 27. 4 cubed is going to be 4 times 4 times 4, which is 16 times 4, which is 64. So this is between 3 cubed and 4 cubed. So it's definitely not a perfect cube. So we're going to end up with a decimal. Now, hopefully you've had a chance to find your cube root button on your calculator. And I'll tell you this, if you haven't found the cube root button on your calculator yet, if you want to take a picture of your calculator and email it to me, I can tell you where the button you're going to have to use is, and I can tell you how to use it, because every calculator is going to be a bit different. And it's really important that you know how to use the cube root button on your calculator. So if you're having issues with the buttons, let me know, because we need to sort that out now. So you're going to use that button a lot in the future. So Taylor's written this is equal to negative, I'm just going to take your word for it, Taylor, 3.1072, and that's just going to keep going on forever. And because it doesn't terminate, it's going to be irrational. Negative 30 is not a perfect cube. So we end up with a decimal. It doesn't repeat. It doesn't terminate. That is kind of the little red flags that say, oh, that's irrational, that's irrational. The last one is 1.21, and this is kind of what I did up above with the 1.75, same idea. What is that 1.21? There's no radical, there's nothing kind of fancy about it, but it's a decimal. And Taylor is written in with a little bit of a question mark. C is rational. Yeah, why? Why is it rational? Remember, we didn't want to talk about anytime we had a decimal it being irrational for this reason. So what makes letter C rational? It is rational. I'll just write down rational. But I need to know the why. So we're halfway there. We have the idea that it's rational, but we need to explain why it's rational. And maybe while you guys are thinking about it, I'm just going to scroll back up to the top. Maybe I'll just keep going. So at the very beginning, we had something, formulas, the area and circumference of pi, which is not a rational number because it cannot be written as a quotient. So we talked about rational numbers being written as quotients. And then we continued on and we said, this is kind of the negative thing that got me a little fired up, but an irrational number cannot be written in the form m over n, where m and n are integers. So if we take the opposite and think about can be written as m over n, that's going to give us a rational number. So can we write 1.21 in the form of m over n? Is it possible to write that as a fraction? How do we write it as a fraction? What does it look like as a fraction? If I were to plug something divided by something into my calculator, how could I end up with 1.21? If I had 121 over 100, that's 1.21. So I can write it as a fraction, and which is great. We also have the fact that Taylor wrote in the right fraction and Anna wrote in that it terminates. So we are kind of both on the right track. Those are both parts of the definition we can use to define these things. So perfect. We can write it as a fraction. So can be written as fraction